Hey everyone, welcome to session 7B of CAV 2020. This is the first session on stochastic systems, and it will have 4 talks. We'll put up the video of the first talk, and the student volunteer has just highlighted on Slack the thread where you can ask questions on this talk, and we will do that for every talk. So the first talk will be by Mingshui Shen on safety of stochastic differential dynamics.
Hello everyone, my name is Mingshui Chen. I'm currently doing my postdoc in Aachen University in Germany within the research group of software modeling and verification. The topic of my talk today will be on the infinite or unbounded time safety verification of stochastic differential dynamics. This is a joint work with my colleagues Shenghua Feng, Bai Xue, and Naijun Zhang from the Institute of Software Chinese Academy of Sciences, as well as Sriram Sankarana from the University of Colorado Boulder. Now I'd like to start the story about the motivation of this work. So we are living in a world filled with stochasticity. In a discrete time setting, with models like probabilistic programs to model a probabilistic choice by rolling a die or flipping a coin, while in the continuous time setting, the so-called stochastic differential equations are usually used to model the continuous evolution of the system state, which is often a random variable equipped with some probability measure. Such a model dates back to the beginning of the 20th century when Louis Bachelier, in his study of the speculation theory, used Brownian motion to model the behavior of a speculator, and thereby the well-known claim that the mathematical expectation of the speculator is 0. As you can see from the animation on the right, the Brownian motion of a particle can be viewed as a 2-dimensional random walk conducted continuously in both time and the space. Then at any time instant, the position of the particle is a random variable respecting to a certain probability distribution. The theory on stochastic differential equations, or shortly SDEs, was later popularized by many researchers, including Albert Einstein and Ito and Stratonovich, who established a rather solid mathematical foundation of SDEs. Since then, stochastic differential equations have witnessed numerous applications, including models of disturbances in engineered systems ranging from wind forces to pedestrian motion, models of biological processes, for instance, the population dynamics of a predator-prey model, and models of financial instruments such as the price of the stock options, as well as the models of robust control where a plant operates against the noisy disturbances from the environment. In particular, over the past 2 decades, due to the fast development of cyberphysical systems or hybrid systems, how to rigorously design or verify safety-critical embedded systems under stochastic noises has become a grand challenge in the realm of computer science and control theory. Good. Now let's take a bit closer look at the SDE model we consider in this paper. Here xt is a vector-valued random variable representing the system state at time instant t. The derivative of xt is the sum over 2 parts. The first part is actually the same as in ordinary differential equations, where b is a vector-valued flow field called the drift coefficient, modeling the deterministic behavior of the continuous evolution. The blue part is the stochastic part, where sigma is a matrix-valued function termed the diffusion coefficient, which encodes the coupling of the system to some Gaussian noise dWt. And Wt is the so-called Wiener process that models the standard Brownian motion. Now, under adequate Lipschitz conditions, the unique solution of the equation starting from some given initial system state x0 is a continuous time stochastic process that satisfies the following integral equation under Ito's interpretation. So intuitively speaking, the solution is a collection of random variables at infinitely many timestamps which is also referred to as a diffusion process. Before introducing the safety verification problem of SDEs, I'm going to give a recap of the problem in the classical setting for ordinary differential equations. There we have an initial set of states x0, which is the blue region here, and an unsafe set of states xu, which is the red area here. Both of them are contained in the system domain X. The safety verification problem asks whether starting from any of the initial states, the system trajectory or solution do not into the unsafe set of states. If this holds for bounded time interval from 0 to t, then we say that the system is t-safe, otherwise t-unsafe. Particularly, we distinguish unbounded time verification with the bounded case by setting the time bound t to be infinity. Good, but when moving into the setting for SDEs, safety verification is no longer a decision problem that seeks for a yes or no answer, because the system trajectory may enter the unsafe set of states with a certain probability p, which means SDE has the probability of 1 minus p to stay in the safe side. Therefore, the infinity safety problem of SDEs aims to bound the failure probability that the solution enters the unsafe set over the entire time horizon from a given set of initial states x0. Notice that here we use the different notation xt2, which is the process that will stop at the boundary of the domain X, as we don't really care how it behaves outside of the domain. To put it in another way, if we denote by the formula phi the property that the trajectory evolves within the domain X, and by psi the property that the trajectory evolves into the unsafe set, then the unbounded time safety verification problem asks for a bound on the probability that the LTL formula phi onto psi holds. The main contribution of our work is a reduction of the infinity safety verification problem to a bounded verification problem. The idea is based on such an observation that for any given time instant t, the failure probability over the entire time horizon can be upper bounded by the sum of the failure probability over the bounded time interval from 0 to t and the failure probability over the unbounded time interval from t to infinity. Notice that this is only an inequality instead of an equality, since there might exist some trajectory that enters the unsafe set in the first parts between the time interval from 0 to t and in the second part from t to infinity, which could be counted twice. On top of this observation, we proposed a set of sufficient conditions under which the second part of the failure probability, which we call the tail failure probability, can be bounded by an exponentially decreasing function in time, witnessed by the so-called exponential stochastic barrier certificate. Such a bound implies that for any given precision epsilon, we can always compute a time instant t such that the failure probability mouse after t can be bounded by epsilon, and hence facilitates the reduction to a t-bounded safety verification problem. Furthermore, for the reduced bounded verification problem, we proposed a more general form of stochastic barrier certificate, namely the time-dependent ones, which can be used to bound the failure probability over the finite time interval. These two bounds together yield an upper bound of the failure probability over the infinite time horizon. As I mentioned barrier certificates, here is a big recap on that in the classical setting. On the left-hand side is the constraints of the barrier certificate capital B, whose boundary corresponds to the dashed curve here in this picture. So it partitions the domain into different parts. While the first constraint says that for the entire set of unsafe states, which is the black disk here in the picture, lies on the positive side of B. And the second constraint says that the entire set of initial states lies on the non-positive side of the barrier certificate. While the third constraint requires that the so-called Lie derivative, which is the left-hand side of the inequality, is negative. This implies that the value of the barrier certificate B along the system trajectory will never increase. Thus, the trajectory of the system starting from the green disk will never cross the boundary of the barrier certificate and escape from the non-positive side to the positive side, and hence proves the infinitesivity of the underlying system. Cool. Now here comes the outline of the technical part. I will first show a set of sufficient conditions on stochastic barrier certificates that enables the reduction of the infinitesivity verification problem to its bounded counterpart. It is followed by a brief introduction on how to synthesize these barrier certificates via convex optimization. Then the effectiveness of the approach will be demonstrated through several examples. And finally, some concluding remarks. We need several ingredients to constrain the barrier certificates, just like the Lie derivative we saw in the previous slide. And here the so-called infinitesimal generator defined for a certain smooth function f plays a key role among these ingredients. Here I won't walk you through the somewhat horrible mathematics, but the key take-home message is that given a diffusion process xt, which is a solution to some SDE, the infinitesimal generator of a function f generalizes the Lie derivative that captures how the function f evolves along the system trajectory xt. With that in mind, we came up with a group of constraints that defines the so-called exponential stochastic barrier certificate V, which is a polynomial function over the system state x. This barrier certificate will later be used to bound the tail failure probability of the system. Here, the first condition says that V is non-negative over the domain. The second condition says that the infinitesimal generator of V along the system trajectory is no larger than minus V itself times a non-negative matrix lambda. Unlike in the classical setting where the Lie derivative is required to be smaller than 0, the infinitesimal generator here is required to be even smaller. And this is actually the key to obtain an exponentially decreasing bound on the tail failure probability, which you will see in a minute. While the third condition is merely used to ensure that the second condition still holds when the process stops at the boundary of the domain. Now let's define a vector-valued function f over time in the system state. If we somehow were able to find an exponential barrier certificate V satisfying this group of conditions, then a nice property of f is that every of its components forms a supermartingale. This means that the expected value of f never increases over time. But because the exponential here is exponentially increasing due to the non-negativity of the matrix lambda, it follows that the expected value of the barrier certificates shall be exponentially decreasing along time. The proof of this theorem is based on Dinkin's formula and Fato's lemma. Now we have a supermartingale f. But in order to talk about the probability over such a supermartingale, Doob's supermartingale inequality comes into the picture. Intuitively speaking, this inequality gives a bound on the probability that a non-negative supermartingale exists some given value over the infinite time horizon. By applying such an inequality to the supermartingale f we've seen before, we can now obtain a bound on the tail failure probability, which is the failure probability over time interval from t to infinity. And here, as you can see in the bound, everything is constant except the time t and the exponent in the denominator. So this bound is actually exponentially decreasing over time. And as I explained, the proof is based on Doob's supermartingale inequality. Such an exponentially decreasing bound on the tail failure probability furthermore reveals the fact that for any positive constant epsilon, there always exists a computable time instant t such that the truncated t tail failure probability is bounded by epsilon. So what left to be done is merely to find a bound on the failure probability over the finite time interval up to t. To this end, we further proposed the so-called time-dependent stochastic barrier certificate, namely the polynomial function h over time in the state space X. This barrier certificate witnesses a bound on the failure probability over the finite time interval from 0 to t. While the group of conditions on h is similar as in the classical setting, the only difference is that we allow h to be dependent on the time t. This is a strictly more expressive form of the stochastic barrier certificate that will in theory produce a non-loser bound on the failure probability, and usually a tighter bound in practice. Again, the proof is based on Dinkin's formula and Doob's Supermartingale inequality. And in fact, we can furthermore simplify the bound by computing an upper bound of the numerator, that is the constant beta, here in this corollary.
Okay, a nice thing about all the constraints previously mentioned for stochastic barrier certificates is that they are all convex. So we can synthesize, for instance, the exponential barrier certificate V by first assuming a polynomial template and then encode its definition as such a semi-definite programming problem, which admits polynomial time algorithms that efficiently solve the synthesis problem. And here the optimization objective actually encodes the tightness of the failure probability bound. The same applies to the time-dependent barrier certificate H, and you can actually find a one-to-one correspondence of these constraints to those in the definition of H. Now I'll present two examples. The first example is an SDE model of the population dynamics subject to some random fluctuations. We aim to bound the probability that the population size grows beyond 2. This is the obtained exponential barrier certificate V, leading to an exponentially decreasing bound on the tail failure probability, which is depicted as the blue curve in the picture. By adding this to the green curve, which is the bound on the failure probability over the time interval up to t, we obtain the bound on the entire failure probability over the infinite time horizon, which is the red curve. In contrast, the dashed line is the constant bound given by a straightforward extension of the barrier certificate method to the stochastic setting. So apparently, our method gives the flexibility to choose a larger time instant that may give a tighter bound. The second example is a harmonic oscillator with some noisy damping, which has a similar experimental results. And for more examples like nonlinear dynamics, please take a look at our paper. Good. To ramp up, we proposed a constructive method based on the synthesis of stochastic barrier certificates for computing an exponentially decreasing upper bound on the tail probability that an SDE system violates a given safety specification. We showed that such an upper bound facilitates a reduction of the verification problem over an unbounded temporal horizon to that over a bounded one. There are several interesting future directions. For instance, the extension to tackle SDEs with control inputs and the infinity safety verification of probabilistic programs, which can be viewed as discrete time stochastic dynamics. With that, I concluded my talk, and questions are welcomed.
Okay, thank you for the talk. Can I just ask that the speaker turns on his video?
Yeah, hello, Alexandra.
Hi, Mingshui. So there are some questions on the Slack. I will read them out loud, and then maybe you can comment on those. Okay. So the first question is from Sebastian Jungs, and is, can you comment on any bounds on the degree of polynomials in Vx and HTX?
Sorry, I was having some net problem.
Can you hear me?
Sorry, yeah, I couldn't hear you clearly. Can you hear me now?
Yeah, I can hear it.
Yeah, it's getting better. So for Sebastian's question on the degree of the polynomials, we don't have a bound on the degree, which means you can set the degree as a parameter when before you do the SDB optimization. But a heuristic there for choosing different degree is that if a degree of a smaller number doesn't work, then you can simply increase the degree by, say, by 1 and try to find a stochastic barrier certificate of higher degree. And if you succeed and you're lucky, then we're done. But otherwise, we can't say anything about that because this is simply a group of sufficient conditions.
Okay, Sebastian's question has a second part. He's wondering how does T occur in H and whether there is some structure to this.
Not really. So T is simply a variable as in the template you set for H. So it's treated as the same as X of the state space. So you basically set a template, a polynomial template with a certain degree and coefficient, and then try to solve the coefficients, and that's it. Yeah.
Okay. Okay, that's great. Thanks. And then there's another question by Majid Zamani, and he asks, why not finding a time-dependent barrier certificate in one shot? One does not need to split the time to a bounded and unbounded domain. Is that correct? Mingshui, did you hear my question? Okay, I think we have lost connection with Mingshui, so I'll ask him to answer the questions on Slack, and given also the time, I propose that we start the next talk.
Yeah.
Mingshui, you can answer the questions on Slack.
Sorry for the network
No, that's
issue.
okay.
I will follow up on Slack.
Yeah, thank you. Thanks, Mingshui. Okay, let's move on to the next talk. Thank you.
Thank you. This is Toru Takisaka from National Institute of Informatics. This is a joint research with Kitty von Farrakhan, Thomas Haas, and Ichiro Hasuo. In this talk, we introduce a novel technique of reachability analysis in stochastic games. Bounded value iteration is a technique to approximate reachability probability in stochastic games. A notable feature of bounded value iteration is that it can approximate reachability probability with precision guarantee. For example, bounded value iteration can answer a query such as compute reachability probability with 0.01% error range. Our contribution is to provide a faster algorithm compared to with the existing one. Faster computation is achieved by performing global propagation, which enables us to omit end component computation that is indispensable for existing algorithms. Let me first explain the problem setting. Our system model is a stochastic game, that is the probabilistic system controlled by two players, controller and adversary. The system evolves in discrete time and has finite states and actions. We are interested in the reachability objective, that is, there is a designated final state and we would like to know the probability of reaching it eventually. Let us see the following easy example, car versus pedestrian. A car is going to pass a crossroad, and there is a pedestrian near the crossroad. The controller, that is, the driver of a car, would like to pass the crossroad without hitting the adversary, that is, the pedestrian, no matter how the adversary behaves. This is a model of the situation by a stochastic game. The game is played in this way. Starting from an initial state, say pedestrian's action in this case, one of the players chooses their action. The active player at each state is determined by the specification. In this example, the adversary is the active player at the state pedestrian's action. Now there are two actions available at this state, stop and pass. The adversary chooses one of them and a transition is made accordingly. If the adversary chooses stop, then the car can safely pass a crossroad and we reach to the goal state. If the adversary chooses pass, then the car must do some evasive action. Such a situation is described by the car's action state, and now the controller chooses their action, brake or honk. The game is continued indefinitely in this way. For each player, their choice of action at their state is called a strategy, which is a map from the player's states to the action set. For example, one possible strategy for adversary is to choose pass at pedestrian's action, and one possible strategy for controller is to choose brake at car's action. Once the strategy of controller and adversary, say sigma and tau, are determined, we can define reachability probability under those strategies as a function from states to real numbers. That is, a function that receives a state S and returns the probability that goal is visited during the play, starting from S under sigma and tau. In the example, reachability probability under the aforementioned strategies has this value. Now our problem is to compute reachability probability under optimal strategy, that is, the function v defined in this way. This definition formalizes our intuition that controller and adversary would like to maximize and minimize reachability probability respectively. In this simple example, we can easily verify that the aforementioned strategies are optimal. But for more complex games, we look for an approximation technique which is computationally feasible. One of the well-known techniques for such a problem is value iteration, which is a fundamental technique in probabilistic model checking or machine learning. In value iteration, we compute an increasing sequence of lower bounds via an iterative computation. It is known that value iteration generates a converging sequence to the true value, but its shortcoming is that without an additional information, we do not know how tight the bound is at each stage. Because of this, it cannot return a sound answer to a query which requires precision guarantee, such as compute reachability probability with 0.01% error range. Bounded value iteration is a variant of value iteration that addresses this problem. The idea is very simple. We also generate a decreasing sequence of upper bounds. By this, we can estimate the error range by taking the difference of upper and lower bounds. We can also return a sound answer to a query which requires a precision guarantee by continuing iteration until the error range reaches to the required precision. Notice that to guarantee termination of such an algorithm, we need to assure that both lower and upper bound converge to the true value. Okay, so now one might wonder that where is the room of technical contribution here? Isn't BVI and technique that merely performs value iteration twice in parallel? The answer is no, it's more than that. More concretely, we need some trick to assure convergence of upper bound. First, let's briefly recall how value iteration updates lower bound for simplicity at controller states. Value iteration alternatively iterates two procedures in the picture. First, based on the current lower bound, value iteration estimates an optimal action at each state according to the value L after a transition. The left picture illustrates that value iteration estimates that action 2 is optimal at the leftmost state. Second, based on the estimated action at each state, value iteration propagates the value of L along the transition arrow in an opposite way. The right picture illustrates that value iteration updates the value of L at the L's leftmost state by backpropagating the value of L according to action 2. Through these procedures, a lower bound L is updated to a new lower bound. This operation is called Bellman update, and the operator that performs this operation is called Bellman operator. So in terms of Bellman operator, value iteration is a procedure that generates this sequence starting from some initial lower bound L0. Now the reason of non-convergence of upper bound can be explained in terms of fixed point. First, Bellman operator is monotone over the set of functions from state set to the unit interval with this constraint. Here, sync state is another designated state from which the final state is never reachable. The partial order of this set is given by the pointwise inequality. It is known that optimal reachability probability is the least fixed point of Bellman operator, that is, V equal mu x holes. Therefore, by clean a fixed point theorem, value iteration generates an increasing sequence of functions that converges to V starting from the bottom element as a canonical initial lower bound. On the other hand, if we start from the top element of the domain, which is a canonical upper bound, then value iteration generates a decreasing sequence that converges to the greatest fixed point of X, which may be strictly above V. In such a case, we have a non-convergence issue. Existing BVI algorithm resolves this issue in the following way. If the system is an MDP, that is, there is no adversary state, then the greatest fixed point can be matched with the least fixed point by merging end components. Roughly speaking, an end component is a part of an MDP that constitute loops. Non-convergence occurs at each state of end components because when we perform value iteration, an upper bound is only propagated inside the end component and information from outside is cut off. It is well known that each end component can be merged into a single state without changing reachability probability. In such a modified system, the greatest fixed point matches with the least one, and the non-convergence issue does not occur. For an arbitrary stochastic game, more involved computation is required because some end components cannot be merged. Instead of that, we periodically perform a singular update over specific end components while running the standard value iteration. Such a singular update is called deflating because it reduces or deflates the value of upper bound over specific end components through propagation from outside. Now we will introduce our novel BVI algorithm. In the previous slide, we saw that every existing BVI algorithm involves end component computation, but it can be a bottleneck of execution time of BVI. It can be particularly influential in the BVI algorithm for stochastic games, where end component computation is required for each deflating procedure. Instead of computing end components, we try to ignore them. End component is problematic in value iteration because it performs local propagation. In other words, it chooses the value to propagate at each state by only looking at possible next states. Because of this, value iteration misjudges that staying at an end component is an optimal behavior. Instead, we globally propagate the value of an upper bound to each state along the path to the final state. In this way, we can naturally avoid being trapped into end components because we enforce the update procedure to refer a strategy that tries to reach to the final state. In what follows, we explain how our algorithm works for an MDP, that is, a stochastic game that is played by controller only. After that, we explain how it is extended for the general setting. First, we need to specify the meaning of a path to the final state, and for each of them, the value to be propagated. To this end, we transform the given MDP and an upper bound into a weighted graph. As an example, let's consider the following MDP and an upper bound U. From this, we first construct a table as shown here. For each state and action available there, the table has an entry which consists of the state, the action, the value of U after a transition, from the state under the action and the set of possible next state. Now we construct a weighted graph in this way. For each entry of this table, we put the state in the first column as the source vertex. We put each state in the possible next state column as the target vertex. We put edges accordingly, and we put the value of u after a transition as the weight of edges. We do a similar thing for each entry of the table and construct a weighted graph. Next, we compute a new upper bound from the weighted graph. For comparison, let's see how the usual value iteration is performed in terms of this graph. What we do is, for each state, we update u with the largest weight of outgoing edges from the state under consideration. For example, there are 3 outgoing edges from initial state with their weight 1, 0.6, and 0.6. Then we update u at initial state by propagating the largest weight among them. Here, we see that the value of u has been converged to 1 at the initial state, while reachability probability from the initial state is clearly 0.6. Indeed, this part of the MDP is an end component, which is the source of non-convergence. Our algorithm instead computes the largest width of path to the final state. Here, the width of the path is the minimum weight of constituting edges. For example, the following paths are all paths from initial state to final state, and their widths are all 0.6. In this example, it would be easy to see that the width of a path from initial state to final state is always 0.6, and thus we put 0.6 as the new value of u at the initial state, which is the true reachability probability. In this way, we globally propagate the width of the widest path to the final state, which is not a single edge in general. Notice that the weight of the loop edge is not propagated here. Its effect is suppressed by the edge to the final state. In this way, our method naturally ignores problematic information from end components. Lastly, the width of the widest path can be efficiently computed by the Dijkstra's algorithm. We explained how our algorithm works for MDPs. Here we briefly explain how we handle arbitrary stochastic gains. Our algorithm receives a stochastic gain and a positive number epsilon, which represent a precision requirement. Starting from canonical lower and upper bound, we update them until their values at the initial state is epsilon close. This structure is the same as any existing BVI algorithm. At each iteration, we update lower bound via the standard value iteration, and then we reduce the stochastic gain into an MDP using the current lower bound as an oracle. This reduction is eventually correct in the sense that for every sufficiently large I, the reduced MDP has the same reachability probability as the original gain. Lastly, we perform our global propagation over this MDP and generate a new upper bound. We proved that by letting the while loop iterate forever, our algorithm generates a decreasing sequence of upper bounds that converges to optimal reachability probability, which means our algorithm always terminates and returns an approximation of V with its error range epsilon. Lastly, we will provide our experimental result. We compared our algorithm with 3 variants of existing algorithm by Kelmendi et al. We tested the algorithms against 13 different stochastic gains generated from 5 models. We observed that our algorithm was fastest in 7 instances out of 13. We also observed our algorithm is stably fast, while every other algorithm is sometimes very slow or fails to finish their computation. As a summary, we introduced a novel algorithm of bounded value iteration, which is faster than the existing one. For future works, we would like to adopt our technique to a general reward setting, as it can only handle reachability objective right now. We would also like to extend applicability of our technique to more complicated systems such as black box fun. So this is end of my talk. Thank you for your attention.
Okay. Thank you, Toru. You can unmute yourself and maybe turn on your camera.
Yes.
Let me just check if there are questions on Slack.
Hi, this is Toru. Do you hear me?
Yeah, I can hear you.
Yeah.
It's okay. I believe, yes, there is one question on Slack from Sebastian Jungs. Does this approach suffer if there are many paths to the final state?
Thank you for question. I don't have a quick question, but the number of the paths in the graph should be certainly relevant to the computation time. Yeah.
Sorry, did you say irrelevant or relevant?
No, relevant. It is relevant.
Okay. Yeah. Okay. I think there are no more questions on Slack, but actually I have a couple of questions, if that's okay.
Yes, please.
You mentioned throughout the talk and then at the very end that you can do reachability at the moment, and that one direction you'd like to extend the work is for other rewards. Do you have already a feeling for what classes of reward functions this might be possible to extend to?
To be honest, we are not very sure about that yet. I mean, how to say, our technique crucially uses the fact that there is a goal in the game, because and then we check the how to say, the widest path to the goal state. So I mean, in the very general reward setting, there is no goal. So I mean, now we are trying to find the how to extend the situation, but
Okay, that's good. I think there are no more questions at the moment, and given the time, I propose that we move to the next talk. Thanks a lot for your talk, Toru, and for clarifying the questions. So the next talk will be given by Cyril Jegorel on global pack bounds for learning discrete time Markov chains. Please go ahead.
Okay, so before jumping into the core of the presentation, I need to make a few recall. So formally, discrete time Markov chain is a triple composed of a set of states, an initial distribution, so in practice it's often a single state, not necessarily, and a transition probability matrix between these states. Discrete time Markov chains are commonly used, notably in model checking, to model the behavior of the stochastic systems. So that's why we want to try to learn them. So, for example, in climatology, we could build from a real system, from a real phenomenon, we could build a theoretical abstraction from some preliminary knowledge or from some preliminary observations, assumptions, or hypotheses. There also exist some academic works on how to abstract a complex CPS, cyber-physical system, as a Markovian system. However, you still need to observe the system and to learn automatically the parameters of this conceptual model. Okay, so in our case, it will be to learn precisely the transition probabilities. This learned model then can be reused for simulations, for verification, or for validation. In this work, we adopt the view of designers of systems for which the probabilities are governed by uncertain forces, for example, the error rates. So we know the structure of the theoretical abstraction of the system, but we do not necessarily know the rates of transitions, the component failures, etc. Regarding the observability, we assume in this work that we can observe sequences of events, so the traces of the system, and the events correspond to states of a DTMC in this abstraction. However, there is often a limited budget for observation and for learning. In trusted machine learning, it is crucial to measure how the learned model differs from the original system and to provide some practical guidelines, for example, on the number of observations, to guarantee some control of the divergence between a theoretical model and a learned DTNC. So this is our goal in this paper. We want to provide some precision and confidence guarantees. So for that, we will use two types of estimation. So standard Monte Carlo estimation and Laplace smoothing. So Monte Carlo estimation works by observing a long run of the system and estimating each individual transition by its empirical frequency. However, in this case, the unseen transitions are estimated as zeros, and this is something that we may want to avoid because the probability of reaching a state could radically change from 1 to 0. So to overcome this problem, we can use Laplace smoothing that consists of adding a positive offset both to the numerator and the denominator of the ratio. Okay, so now we know how to estimate an individual transition, but how do we guarantee that the system, so more precisely the theoretical model, and the learned model are close enough after some observations? Basically, we need a stopping criteria to tell us whether we have done enough observations or not. So a naive approach could be to use the Chernoff-Okamoto bounds to guarantee for all transition that the probability of deviation between an individual transition probability and its estimation do not exceed epsilon with probability more than 1 minus delta. So for recall, the Okamoto bound tells you that for any epsilon delta and probability gamma, you can control the deviation between this probability gamma and its binomial Monte Carlo estimation by setting the number of samples above this formula. So note that this bound is inversely proportional to epsilon square and to log delta. And thus estimating precisely all the transitions up to epsilon delta might be unrealistic in the case of large system and also potentially unnecessary. Moreover, it does not necessarily guarantee similarity between the behaviors of the system and the model. That's something we will see later on. So we need to change this notion of distance and between individual transition and the estimator, and to replace it by something else to guarantee that our system and the learned model are close enough, meaning that they have a similar behavior where the behaviors are some properties specified using temporal logic. So mathematically, it means close enough means that the probabilities of the behaviors are equal in the original and the learned models up to precision epsilon with confidence at least equal to 1 minus delta. We will make use of two different logics in this talk, linear temporal logic and computation tree logic. So linear temporal logic, LTL, is defined by the following grammar: atomic proposition, true, false, negation, conjunction, disjunction, and finally, globally, next, and until operator. For state CTL, we have a set of state names, and our proposition will be preceded by a quantifier on paths, all or there exist, followed by a path-specific quantifiers. So next, globally, until, or finally. And here, as we want to compute the probability of paths satisfying a CTL formula, we basically remove the path quantifier operators. So for all and there exists, we don't need them. And we consider the set of path CTL formula, that is formulas of the form next phi1, finally phi1, globally phi1, or phi1 until phi2, with phi1 and phi2 two-state CTL formula. Note that some properties can be expressed in CTL but not in LTL, for example, AG phi, or some properties can be specified in LTL but not in CTL, for example, FG phi cannot be expressed in CTL, but can be expressed in LTL. So we have formalized everything we need. We can now restate our problem. So our goal is to provide a learning algorithm such that for an arbitrary temporal property phi, given some epsilon and delta, we can control with high confidence the deviation between the probability of occurrence of this property under the original system, A, and the learned model, A hat. So not that in this inequality, we are comparing two exact probabilities. Here, the randomness doesn't come from the probability of occurrence of the property, but from the model itself. We are working under some assumptions. So since we designed the system, we know the graph of transitions, but we do not know the individual transition probabilities. Moreover, my second comment here is not really an assumption, but more a difference between other approaches. In our work here, we do not need to know a lower bound on the positive individual transition probabilities, which is often an assumption necessary in the other approach. So our first contribution was to answer the following question. Can we learn a model such that after some finite time, any LTL formula probability is close enough in the original system A and in the learned model up to some epsilon delta? So the answer to this question is no, it's not possible. And here is a sketch of the proof. So let UV be a probabilistic transition and tau be an offset between the probability AUV and its estimation. And let phi k be the following property. So transition UV occurs at most a number of times equal to AUV plus tau divided by 2, the whole divided by k, during the k first visits of state U. You can prove that phi k is a LTL property. If I'm not wrong, it's a conjunction of nested next properties. And under A, the probability of phi k tends to 1 when k tends to the infinity. But under A hat, the probability of the property phi k tends to 0 when k tends to the infinity. You can prove that using the law of large numbers. So a single deviation between a model and the original system can cause a deviation, a complete deviation of the probabilities of occurrence of some well-chosen LTL properties. However, can we still provide some guarantees for some particular subset of LTL? So actually, yes, we can still provide a learning algorithm that outputs a matrix that is accurate for TTF, for time to failure properties. So the time to failure properties are the properties of leaving a particular state and reaching a final state or a failure state without repassing by the initial state. They are quite important, notably to compute the mean time to failure. I won't give the complete proof of this result, but basically, the first step is to show that you have an equality between a Monte Carlo estimator based on a sample set W and the exact probability of phi under the model built after W. Then you can inject the Monte Carlo estimator into the inequality. You can replace the exact probability of the model by this Monte Carlo estimator and apply the Okamoto bound. So note that in general, this equality is not true for other properties than the time to failure properties. Moreover, for time to failure properties, since we have this equality, our approach is at least as good as statistical model checking. So what I mean here is that if you want to estimate the probability of some property, well, you could in parallel learn the model as we did, in order to estimate as well the model. It won't cost you more observation, basically. So let me show you how the algorithm works in detail. So we start with an unknown but observable system A, an initial state S0, a final state SF, and the delta and epsilon, the confidence and precision parameters. We generate paths starting from S0, and once they reach S0 or SF, we output a Z value, which is equal to 0 if we reached S0, or 1 if we reached SF. And on the fly, we update the number of paths, the number of success, and the path, of course, and the matrix of transition. And we repeat this procedure until the number of paths satisfies the Okamoto criteria. At that point, the matrix, AW, will be accurate for the time to failure property. Finally, we have a third result, a third contribution. So we are working under the same assumption than before. We know the graph of transitions. However, now we assume that W is obtained by observing traces until a state is seen twice on the trace. So basically, the traces are loop-free paths. And we assume that we have some kind of reset mechanism to reobserve from S0. So our contribution is the following. We can now learn a model A hat such that after some finite time, for any CTL property phi, we have a probabilistic bond over the deviation between the model and the original system of the probabilities of these CTL properties. The proof is quite technical, so please have a look on the paper if you want more details. Here I will only go through it quite quickly. So we need to introduce eta, which is an offset between two Markov chains, A and A eta, and a conditioning term called CLSF in this slide, because we need them to prove that for any phi of the form S0 until SF, we have a bond over the difference between A eta and A. Moreover, all the properties can be expressed as S0 until SF for a well-chosen S0 and SF. Interestingly, to prove our third result, you need to use Laplace smoothing when you do the learning. And if you choose well the Laplace smoothing parameter, alpha I, you can actually also bond the statistical error caused by the Laplace smoothing. Then, using triangular inequality, you can prove this probabilistic bond here, and then apply the theorem 5 to bond all the probabilities of the property of the form S1 until S2. That is, all the past CTL properties. So after a few optimizations, for example, we replace the Okamoto bond by the Massar sequential bond, we finally output a stopping criteria for the number of observations, guaranteeing a matrix accurate for the whole CTL. So here is the algorithm. To evaluate our approach, we first created some crafted models with different specification. For example, one system was containing rare states, and we evaluated how many events were sufficient for learning an accurate DTMC for a time to failure property and for the whole CTL. In the second set of experiments, we evaluate on large prism models. And the goal here was to learn a matrix accurate for a given property and to compare with hypothesis testing. So we repeated each algorithm 100 times except for system 4, and we reported the average number of events. Note that we are still able to learn a matrix accurate for CTL with more than 40,000 stochastic transitions. And some systems, like the system 4, are more difficult to learn because they contain rare states. So to conclude, we provided 3 contributions. First one is that there is no learning procedure outputting after a finite time a DTMC model accurate for all LTL properties, but we can still provide an algorithm that outputs a model accurate for a given time to failure property. Moreover, we also provided an algorithm based on Laplace smoothing that outputs after a finite time a DTMC model accurate for all CTL. As a future work, we are considering improving our optimizations and considering also other logics or subset of CTL, subset of LTL. The right states also remain problematic, but we foresee some solutions involving maybe rare-event simulation. Thank you for your attention.
Okay, thank you for your talk. Can you please unmute yourself and maybe turn on the camera? Okay, thank you. Let me see if I can just highlight your video for a moment. Let's give a couple of minutes to see if people have questions on Slack. So there's one question already on Slack from Muhammad Sardar. Do you have any plans for energy utility quantile properties?
For energy utility what?
Quantile properties. I'm not quite sure what quantile means.
I mean, I'm not aware about this these properties in particular, but so no, I don't have a particular plan for that. But I'd like to hear more about it.
Yeah, so maybe Muhammad can then say more on Slack, and you can later check. I'll continue reading some of the other questions. So Sebastian has a question. If I understand you correctly, you are learning transition probabilities. Yeah. Can you somehow compare these two approaches that do parameter synthesis?
I mean, to compare with which technique in particular, actually?
I'm gonna take a guess here and imagine that he's referring to the work of Jan Kretinsky, but this is me guessing. This is me guessing. I'm totally guessing here. So
yeah. So okay, I haven't read the most recent work of Jan, and I mean, but actually we used their work in this paper actually for proving notably the first result.
So is there? So following up on that, is there a common sort of technique that applies to both transition matrices and parameter synthesis? Is there a common sort of framework in there?
There was some difference. Actually, we also use their test suite in our evaluation, but I can't remember why. But there was many things we could not compare with them, and also I think they have an assumption of a lower bound on the transitions on the transition probability, which is an assumption that we do not have in our.
Sebastian clarified what related work he meant. There is work by Alessandro Abate on base learning parameters, and then lots of work by Jos-Pieter Katoen and others that ask for which transition probabilities certain properties hold.
Okay, I take notes, but no, we haven't compared with this work.
Okay. I suggest you look at the Slack later, because there's some very interesting comments and references that Sebastian is making. So maybe you would like to.
Are they estimating Markov chains really, or are they estimating probabilities of properties, which is fundamentally different in our case?
So I believe from the description Sebastian is giving that they are doing the opposite, right? So they start with the property and they ask for which transition matrix would this property hold, I believe. So I think it's more connected than it might sound at first instance. So I suggest you look on Slack. I'll ask one last question before we move on, and then there are many questions on Slack, so I really suggest you look later. But there's one more question from Shibashis Guha. Could you give an idea if the approach can be used for quantitative properties like expected long-run average?
Expecting long-run average. That's more tricky because expecting long-run average. That's a bit difficult to answer that on the spot, but I guess if you are, once you have learned the matrix of transition, you could use it to calculate exact. I mean, with exact methods, you could calculate some expected values. But if the model is really large, and if there are a lot of paths, I think that might be still really difficult, I guess.
Yeah. And did you look at MDPs as well, or just Markov chains?
Just Markov chains.
Okay. Yeah. Okay. I propose we stop here the discussion because we're a bit over time, and that you take this on Slack. Okay. Yeah. So on to the next talk that will be on statistical model checker with stratified and antithetic sampling. Go ahead.
Hello everyone, in this talk I will talk about STMC, a statistical verification tool we recently developed to lower the number of samples and hence have a more efficient statistical verification algorithm. My name is Nima Ruhi and this is a work in collaboration with Yu Wang from Duke University and Matthew West, Geer Delarue and Mahesh Viswanathan, all from University of Illinois at Urbana-Champaign. I have already said that STMC is a statistical verification tool, so it is dealing with probabilistic systems. But as a very short introduction, why allowing probability in our models in the first place? This is because allowing probability in our models lets us have more realistic representations, models that are closer to the real phenomena. For example, we can model noise in sensors and robots can build probabilistic belief about their surroundings. Also, as soon as we have probabilistic models, we can have probabilistic properties too. Am I dealing with a fair dice? Or is it true that probability of a severe accident is very small? Now that we have a probabilistic system and probabilistic properties, in principle we can use symbolic techniques to verify those properties. At least in theory, and I will get back to what I mean by at least in theory, using symbolic techniques we can compute the exact answer. But the deal breaker is that they are often too slow to be used in most practical situations. This is where a statistical verification comes in. By statistical verification, I mean verification by randomly simulating executions of the system. It has its pros and cons. The best thing about a statistical verification is its scalability, but it has other benefits. For example, if all I want is the ability to simulate executions of a system, I can look at the system as a black box. I don't really need to know the dynamics, and I don't need to know a closed form of probability distributions. A statistical verification has its own set of problems. First and foremost, because it only looks at a finite number of executions of a system where there are uncountably many of them, the answer could be wrong. It assumes access to random number generators, but in the implementation, we often only have pseudo-random number generators. Because we care about performance, simulators often ignore errors introduced by floating point arithmetic. Because we only look at finite number of executions, we cannot differentiate strict and non-strict inequalities, and for the same reason, in general, we cannot handle equal and not equal probabilistic properties. The most fundamental step in a statistical verification is taking random samples, but we also need to know when to stop sampling. This termination condition is often defined using sample variance. The smaller the variance, the fewer number of samples. A stratification is a sampling technique that tries to reduce the sample variance, and if it succeeds in doing so, then we have a more efficient verification algorithm. To see an example, suppose we want to take hundreds of samples from a unit square. If these samples are independent of each other, for each sample, I take two random numbers from the interval of 0, 1, one for the x-axis and one for the y-axis. Since all these samples are independent from each other, it is quite possible that some of these little boxes in this picture receives no sample and some other receive multiple samples. In the stratified sampling, however, I first divide the support into small boxes and then take one random sample from each of those boxes. So within each box, the location is probabilistic, but each box receives exactly one sample. As you can see in this picture, the stratified samples are scattered more evenly. Stratification can be used to take samples from other distributions as well. I have a picture here for exponential distribution, but in the interest of time, I won't talk about it today. Each sample in the previous slide only requires 2 random numbers. That is why I could divide each axis into multiple subintervals and consider all possible combinations. However, this is not always possible for temporal properties. First, the number of steps is not always known a priori, and even if we do know that number, it is often much larger than 2. For example, if each execution involves 100 steps and we only divide each step into 2 subintervals, then the stratification approach I took in the previous slide requires 2 to the 100 samples, which is not feasible. However, it is still worth trying to take stratified samples. In both of these videos, we see estimated distribution probability of robots at different steps in time. Samples in the left-hand side are taken independently, and samples in the right-hand side are taken using stratification. It is easy to see that stratification gives us much better estimation. The major problem is that in general, we cannot take stratified samples with this high quality efficiently. In fact, to take stratified samples in this small example, I am doing a lot of computation. So in general, one has to use some heuristics on how to take stratified samples. That is the main focus of our tool STMC. It supports both discrete and continuous time Markov chains as probabilistic models. It is built on top of Prism, so it supports any model that Prism can simulate against any temporal formula that Prism can evaluate on single executions. We ran our algorithm on quite a few examples, from tens of millions to more than 100 terastates. These experiments show that our algorithm reduces the average number of samples more than 3 times, and this is in comparison with sequential probability ratio test SPRT, which is known for its superior performance. And finally, everything is open source and already published. For the experimental evaluation, we ran different algorithms on different examples, 10 different examples, each with 4 different sets of parameters. Here is one of those 40 cases. The left-hand side is the average time, and we ran each statistical algorithm 20 times. The first 4 are symbolic algorithms implemented in Prism. Either they ran out of memory or they did not terminate after 30 minutes. I've already mentioned SPRT. In order for SPRT to be as efficient as possible, there are some assumptions that are not satisfied by our examples. GLRT is an algorithm that tries to solve this problem of SPRT by not requiring those assumptions. However, in our examples, it is not very successful. Antithetic sampling is another verification technique that we have implemented. However, in the interest of time, and since in our experience it is not as powerful as stratification, I did not talk about it. The rest is stratified sampling. We tried different number of strata, 216, 256, and 4096 strata. When we have more than 2 strata, we consider different possibilities to divide a strata over different steps. For example, 4000 to the power of 1 means every step 4000 strata, but different steps are independent of each other. But 2 to the 12 means that every step only 2 strata, but all possibilities in combining these 2 strata over every 12 steps are considered. You can see that when 4000 to the power of 1 strata are used, we have almost 4 times reduction in the average time and 8 times reduction in the number of samples. And finally, what we have here in the left-hand side is the average number of samples. We see that when 4000 strata are used, the average number of samples is reduced more than 3 times. On the right-hand side, we see the success rate of different algorithms. Success rate of statistical algorithms being 100% and success rate of symbolic ones not being 100% for large examples is as expected. There are a couple of reasons in our paper for why this comparison is still useful. Here is the most important one. Remember that I said symbolic verification techniques give us the precise answer, at least in theory? Well, it turned out that even to have this much success rate, they apply some kind of heuristics for their termination condition, and it is known that those conditions do not guarantee a correct answer. What this means is that the error guarantee we get from statistical algorithms is stronger than the error guarantee we get from the implementation of symbolic ones. Thank you for listening. A member of our team would be happy to answer your questions.
Okay, thank you very much. I know Wang is ready to answer questions. In view of time, I'm going to propose that we take questions on the tool paper on Slack. Since there are no questions there already, I propose people do discussion offline because we're supposed to be running already the last paper of today. So apologies to you, but if you can link on Slack and people will leave questions there and we can do the discussion.
Yeah, of course. Yeah, thank you.
Thank you very much. So the last paper of this session is a paper that will be presented by Kiran, and we joint work with Ilya Sergey.
Hi, I'm pleased to present our research, Ceramist, Certifying Certainty and Uncertainty. So, there's this rather nifty feature of many modern web browsers, that is that when you click on a URL that's known to be malicious, the browser will show a little pop-up indicating that the URL should not necessarily be trusted. Now, this is a pretty invaluable feature, however, its implementation raises a couple of interesting questions. In particular, how exactly does a browser know that a given URL is malicious? Because on one hand, trying to store the set of all known malicious URLs locally is something that is just practically infeasible. Conversely, sending every URL that you browse to an external server is something that most people would take issue with. So browsers actually implement this by means of a rather interesting compromise. They use a data structure known as a Bloom filter to store a space-efficient local approximation of the set of all known malicious URLs. Now, by querying this local approximate set, the browser will only send up a URL to the external server if it has a relatively high likelihood of actually being malicious, thereby preventing unnecessary infractions on user privacy. Now, this feature, which safeguards the privacy of millions and millions of users throughout the world, depends on two key properties provided by a Bloom filter. The first, a no false negatives property, essentially states that the Bloom filter will only return a negative result, i.e. that a given URL is not in the set of malicious URLs, if it is actually in fact honest. In other words, the Bloom filter will always catch malicious URLs. The second property, a low false positives rate, essentially states that for any honest URL, the probability that the Bloom filter will return a positive result, i.e. that the URL is in the set of malicious URLs, will be relatively low, thereby minimizing the number of unnecessary infractions on user privacy. Now, this system works quite well, apart from one small issue, and that is that the widely cited expression for the false positive rate of a Bloom filter is in fact wrong, and has been the subject of around 30 years of mathematical contention and has required several corrections. Our research tackles this problem by deriving the first certified proof of the false positive rate of a Bloom filter and extending our proof strategies to apply to a wider class of probabilistic data structures, thereby potentially preventing these kind of errors from happening in the future. In the rest of this talk, I will give an overview of this research. We'll first look at what exactly Bloom filters are and how exactly this original error ended up occurring. Next, we'll look at how we managed to encode Bloom filters in Coq and prove these corresponding properties. Finally, we'll discuss how we can generalize these proof strategies to apply to other data structures. Okay, so what exactly is a Bloom filter? Well, put simply, a Bloom filter is just a bit vector paired with a sequence of hash functions. In order to use the Bloom filter as an approximate set, when you want to insert an item, you hash it over each one of the hash functions, and treating the hash outputs as indices into the bit vector, you raise the corresponding bits. Notice that the hash outputs may overlap, and so the number of raised bits may be less than the number of hash functions. Now, conversely, when you want to perform a query, you take your input, you hash it over each one of the hash functions, and treating the hash outputs as indices into the bit vector, you check whether the corresponding bits are raised. If all of the bits are raised, then the value is in the Bloom filter, and otherwise it is not. Now, these properties are fairly simple, but if you think about it, you'll be able to see that actually these are enough to ensure the no false negatives property. Intuitively, this occurs because when you insert an item into the Bloom filter, you raise a certain set of bits, and there are no operations that can ever unset these bits, so any subsequent query for that item must return true. In other words, the only way you can get a negative result is if you had never inserted that item before. Now, this is the case with negatives. However, things get slightly more interesting when you look at positives, because there is a possibility of false positives. To see why this is possible, consider the following example. Suppose we insert a value x into the Bloom filter, and it happens to map to the following set of bits. At a later point, we may want to query for a different value y. Depending on the choice of hash functions, there is a possibility that y may map to a subset of the bits that x maps to. And in this case, our query would return positive, even though y is not in the Bloom filter, i.e. we would get a false positive. Now, ideally we'd like to characterize the frequency at which these kinds of results can occur. However, this is going to be highly dependent on our choice of hash functions. So the standard way of performing this analysis is to assume that each one of the hash functions are chosen uniformly at random, and with this assumption we can then reason about the false positive probability. This is, after inserting n elements, what is the probability that we get a false positive result? In Bloom's original publication, he proposes the following derivation for the false positive rate of a Bloom filter. Now, to simplify the analysis, we'll begin by looking at the changes and behaviors of a single bit in the bit vector as we perform insertions and generalize from there. When we hash a value over a single hash function, as the hash outputs are uniformly random, the probability of the hash output being our selected bit is simply going to be 1 over the number of bits, 1 over m. Naturally then, the probability that the hash output then misses our selected bit is going to be 1 minus 1 over m. Additionally, as each one of the hash functions is independent, they all have the same probability of missing our selected bit. And so the probability that they all miss our selected bit is simply going to be this expression raised to the power of k. Extending this independence argument even further, the probability that after inserting all n elements, all of the hash function invocations miss our selected bit is simply going to be raising this expression to the power of n. So this is the probability that after inserting n elements, the hash functions fail to hit our selected bit. And so naturally the probability that they do hit our selected bit is simply going to be 1 minus that expression. From here, Bloom reasons that in order for a false positive to occur, all of the bits that your queried input maps to must also be raised. And so, assuming that the bits are all independent, the probability that this occurs is simply going to be our expression raised to the power of k for each one of the k hash functions. And this was the bound that he gave in his original publication in 1970, and here it is in the paper. And shortly after it was published, it became a mainstay of engineering applications, and the bound was replicated in paper after paper after paper. Unfortunately, it turns out that this bound is wrong, and this was noted by some subsequent researchers 30 years down the line, who noticed that Bloom's assumption that the bits are independent is actually incorrect, and fails to account for certain interdependencies between the bits. The researchers also came up with a novel derivation for the false positive rate of a Bloom filter. However, unfortunately, 2 years down the line, it was found that this also had errors in terms of incorrect definitions. So clearly this field is in dire need of some formal verification, and this was the primary impetus for us to start considering how we might go about encoding Bloom filters in COC. Now, with regards to encoding probability, we chose a fairly standard approach. We used a probability monad to encode random outcomes, and then using this we were able to express hash functions as random oracles. When hashing a value that has never been seen before, the output is a perfectly random value, and when the value has been seen before, then the output will be the same as the output returned from the first invocation. This is tracked by this additional hash state parameter. When we moved on to the encoding of Bloom filters, we made a rather interesting observation, and that was that we were able to decompose the behaviors and implementations of Bloom filters into modular reusable subcomponents, in particular by splitting on whether we were dealing with the probabilistic or the deterministic aspect of a Bloom filter. The probabilistic aspect being the process wherein we take our input, we hash it over a sequence of hash functions, and the deterministic component being the process wherein we take these hash outputs, treat them as indices into the bit vector, and we either raise the corresponding bits or query them when we're doing queries. The nice thing about this decomposition is that it quite closely follows our natural intuition for many of the proofs. For example, when I told you about the no false negatives property, I mentioned that the intuition for why it holds is because when you insert an item into the Bloom filter, you raise a certain set of bits that can never be unset. If you think about it, this property is primarily a deterministic one, and it turns out that when we were implementing the corresponding proof in COC, we were able to prove it by looking purely at the deterministic component, thereby allowing our proofs to generalize to arbitrary choices for hash functions. In this way, we were able to produce the very first certified proof of the false positive rate of Bloom filters as being the following gnarly expression there, putting an end to 30 years of mathematical errors, and finally restoring some certainty to a mechanism that we use every single day. So additionally of note, the curly braces in our expression refers to the combinatorial operator known as Stirling numbers of the second kind, which we also produced one of the first certified proofs of. So this was quite a nice result. However, it was also quite a large undertaking. And so we were interested in seeing whether it was possible to generalize some of the insights, and maybe even some of the proofs from our analysis, to other data structures in the area. And when we started looking at the related literature, we started noticing some rather interesting structural similarities. A particularly egregious example is the case of counting Bloom filters, which have almost the same structure as a Bloom filter, but rather than using bits, they use counters. These kind of similarities seem to suggest the potential for proof reuse when we attempt to verify these data structures in CAV. And in fact, zooming out from Bloom filters, it turns out that these structural similarities we noticed are actually shared by a larger class of probabilistic data structures known as approximate membership query structures, which are a class of probabilistic data structures that provide space-efficient encodings of approximate sets of objects, much like the Bloom filter does. So the natural question is it possible to apply our analysis to these data structures to verify them? And what we found is that yes, actually it is. We found that our decomposition of decomposing data structures into probabilistic and deterministic components seems to apply to most AMQs we could find. And when we were able to apply this decomposition, we were able to obtain massive proof reuse between these data structures, and sometimes even derive certain properties for free. To give an example of how exactly this works out, let's have a look at how we managed to verify the properties of a counting Bloom filter, building on our results from Bloom filters. So the counting Bloom filter operates quite similarly to a normal Bloom filter. When you want to insert an item, you hash it over each one of the hash functions, and treating the hash outputs as indices into the vector, this time instead of raising the bits, we increment each one of the counters. Similarly, when you want to query, you hash the input over each one of the hash functions, and treating the hash outputs as indices into the bit vector, rather than checking whether each one of the bits is raised, we check whether all of the corresponding counters are greater than 0. So immediately you should be able to see some quite striking similarities between the logic of this implementation and that of a Bloom filter. And thankfully, our analysis technique allows exploiting this. So immediately, when we start decomposing the behaviors of a counting Bloom filter into its probabilistic and deterministic components, notice that the probabilistic component, the process of taking an input and hashing it over a sequence of hash functions, is exactly the same as the corresponding probabilistic component for a Bloom filter. So noticing this similarity, we can essentially just copy over that entire section from the Bloom filter over to a counting Bloom filter, allowing for massive proof reuse. So this is pretty useful, but it gets even better. If you think about it, there are actually some additional similarities in the logic between counting Bloom filters and Bloom filters that we haven't exploited that rise in the deterministic components. In particular, when we query a counting Bloom filter, we don't look at the entire value of the counter. We look at a fairly simple binary property of the counter, whether it's greater than 0 or not. And viewed from this perspective, we can see that the behavior of a counting Bloom filter is essentially just a superset of the behavior of a Bloom filter. So there is still a notion of certain bits being raised. However, it just so happens that we are now tracking some additional information in the form of the exact number of times the particular element has been incremented. And exploiting this similarity, our proof strategy allows us to carry over all of the proofs from the Bloom filter by requiring that we only derive a fairly simple reduction between the deterministic state of a counting Bloom filter to the deterministic state of a Bloom filter, allowing us to obtain most of the important properties with little to no effort. We package together our findings into a reusable framework. We define a set of interfaces to capture the abstract properties shared across AMQs, and then define many of our proof strategies in terms of functors acting on these interfaces. In this way, any future AMQs that meet our interface definitions will be able to reuse many of our proof strategies, thereby reducing the burden of verification. Additionally, we instantiate these interfaces for a variety of commonly used AMQs and produce a zoo of AMQ components that can be mixed and matched together to produce arbitrary custom AMQs. In this process, we even happen to construct several entirely novel AMQs by composing these components in interesting ways. This wraps up the state of our development as it is today. However, with regards to ways in which it may be extended in the future, there are several directions that show a lot of promise. One such interesting idea is to try and extend this framework from applying only to approximate membership probabilistic data structures to also support approximate counting structures. We've noticed that there are some quite interesting structural similarities between counting Bloom filters that we have verified and count-min sketches, which are actually used for approximate counting. Another idea is that now that we have this formal definition of the behaviors of a Bloom filter, there seems to be potential for automatically inferring the kind of optimizations we saw in a browser. Perfect. So this wraps up my talk. Thank you for your time. I'd be pleased to take any questions.
Okay, thank you, Kiran. Maybe you can unmute yourself and turn on your camera. So there is one question on Slack. Shriram says that he teaches the wrong proof to his student in algorithms. And is it the case that the proof is wrong, or does it use some assumptions, some independence assumptions that are not justified?
So actually the original proof by Bloom is actually just incorrect. So when we initially started sort of verifying this data structure for about a month, I was trying to prove his original bound, which is rather painful. And then sort of a month into this, I realized that I found this other paper, the 2008 one. And so actually the issue is that in exactly the same way that I showed you, that there are no assumptions that could actually make his derivation correct. It's just the bits are not independent, so you can't you can't take that final power to the power of k, because in the simplest sort of counterexample would be that if all the hash functions happen to map to a single bit, then the probability that you get a false positive is just going to be sort of 1 over n. So it's just going to be the probability that any one of the hash functions happens to hit that selected bit. And so yeah, it's okay. Just sort of wrong.
Thanks. That's a very clear answer, very instructive. Since we are already sort of into the break, I propose that the other questions are taken offline on Slack, if that's okay with you. I think you're on Slack and you see the thread there. So I'll sort of wrap up this session. Thank you very much to all the speakers for staying in for discussion and for the lively discussions also on Slack. And if you go to the main announcement track on Slack, you will see the link for the breakout Zoom session, and that has started a couple of minutes ago. So I hope to see some of you there. Thank you very much.